Look up at the night sky tonight. It appears serene and constant, a tiniest tapestry of silent lights. But this tranquility is an illusion. We are living through a revolution in cosmology. An explosion of discoveries is shattering our understanding of the universe. In the last few months alone, we have witnessed events that defy explanation. An interstellar object of impossible properties is approaching Mars. Evidence of ancient life on the red planet has passed peer review. The James Webb Telescope is seeing galaxies that should not exist. Gravitational wave astronomy is hearing the echoes of cosmic collisions. Private companies are racing to mine the moon. This is not science fiction. This is October 2025. The universe is revealing itself to be stranger, more violent, and more magnificent than we ever dreamed. And the pace of discovery is accelerating so fast that yesterday's headlines are already obsolete. In the next hour we will connect all these dots. From the interstellar anomaly screaming past Mars, to the ancient mudstones of Jezero crater, from the deepest images of the early universe, to the new space race for lunar resources. Some of these stories were buried by mainstream media. Others were reported without understanding their implications. A few they are actively trying not to talk about. This is the cosmic news they do not want you connecting together. If you are ready to see the real picture of our place in the cosmos, and hit that like button and subscribe, then tell me in the comments where you are watching from and what the sky looks like tonight. Let us begin. In exactly 40-8 hours, something extraordinary will happen at Mars. An object from the depths of interstellar space will make its closest approach. It is traveling at over 130-7,000 miles per hour. It will pass within 18 million miles of the red planet. And for the first time in history, we will photograph it with unprecedented resolution. But here's where the story defies all logic. This thing is 30-3 billion tons. That is 3 to 5 orders of magnitude heavier than any interstellar object ever found. It has no visible tail even though it ejects 150 kilograms of material every second. Its glow points forward against its direction of travel, which should be impossible. It emits nickel in its spectra without any trace of iron, violating basic chemistry, and its trajectory is perfectly aligned with the plane of our solar system, a statistical miracle. Harvard's Avi Loeb, the same scientist who studied the MUA gives this object the 6 out of 10 on his scale for being potential artificial technology. Not a 1, not a 2, a 6 out of 10. Meanwhile, multiple spacecraft are coordinating for a desperate observation campaign. The Mars Reconnaissance Orbiter is reprioritizing its entire schedule. The Chinese Tianwen-1 probe is aligning its cameras. The European Space Agency's Mars Express is joining the effort. All will capture images at 30 kilometers per pixel resolution. For the first time, we will separate the nucleus from a surrounding dust cloud. We will see its true shape and surface features. We will know if it is tumbling randomly or rotating in a controlled manner. This opportunity will not come again. 3-Psi Atlas is moving at interstellar velocities. After it passes Mars, it will dive toward the Sun, reaching Pearl on October 20-9. Then it will be flung back into the dark forever. We get one chance, one single window, and that window opens in 2 days. The latest date from Dr. Loeb's team is critical. A new peer-reviewed paper analyzed over 4,000 observations. It found no detectable non-gravitational acceleration. None. This object is spewing material like a continuous rocket engine, yet its path is dictated purely by gravity. The residual acceleration is less than 100,000th of Earth's gravity. How can you have massive thrust with zero deviation? The answer is an absurdly massive object. The thrust is negligible against its immense inertia. The calculations point to a minimum mass of 30-3 billion tons. That implies a solid nucleus at least 5 kilometers in diameter. Here is the problem that breaks the natural model. Where do 30-3 billion ton interstellar objects come from? The statistical reservoir of interstellar rocky material is limited. The odds of such a massive object entering our inner solar system are vanishingly small. We should see one every 10,000 years. Yet we found this on our third try. The statistics are shattered, the model collapses. Unless the size distribution we assume is wrong. Unless 3-Psi Atlas is not a random chunk of ice and rock. Unless it is something else entirely. Then there is the chemistry. Nickel without iron is a signature that should not exist in nature. The two elements are chemically married, formed, and sublimated together. Yet the spectrum of 3- by Atlas shows clean nickel lines and no iron. This is not a measurement error, it is a stubborn fact. Stack these anomalies together. The impossible mass. The paradoxical thrust. The unnatural chemistry. The fine-tuned trajectory. Each one is odd on its own. Together they form a pattern that screams for alternative explanations. Avi Loeb's 6 out of 10 rating is a serious scientific statement. It means the evidence compels us to consider all possibilities. In 2 days, the cameras on the Mars orbiters will give us an answer. If the nucleus is larger than 5 kilometers, the natural explanation becomes untenable. If it is small and shrouded in dust, that may just be a very strange comet. October 3rd will be a day we remember. We are about to learn something profound about our neighborhood, whether we are alone or surrounded by cosmic artifacts. While the world watches the sky, another revelation sits quietly on the Martian surface. Inside a sealed tablet is a rock sample nicknamed Sapphire Canyon. 3 weeks ago it passed the most rigorous test in Science peer review. On September 10, 2020-5, the journal Nature published the findings. The paper describes a rock collected by the Perseverance rover in July 2020-4. Its official name is Jezero, named after a waterfall on Earth. The rover found it in the Bright Angel Formation, an ancient river delta in Jezero crater. The rock's surface is covered in Leopard-like spots, patterns of pale white, deep black, with streaks of green and blue. On Earth, such patterns form where chemistry and biology intersect. The rover used its sophisticated instruments to investigate. PIXL, the planetary instrument for X-ray lithochemistry, mapped the elemental composition. SHERL&C scanning habitable environments with Riemann luminescence hunted for organics. What they found reads like a recipe for ancient microbial life. First, the rock is a fine-grained mudstone. This type of rock forms in calm water environments like lake beds. It is a perfect preserver of biological signatures. Second, the chemical composition is rich with life's building blocks. They detected oxidized iron, essentially rust. They found phosphorus, a key element, in DNA and RNA. They identified sulfur in multiple forms. And they confirmed the presence of organic carbon molecules. The distribution of these elements is what matters most. The leopard spots are concentrations of specific minerals, vidionate, E and Greek E. These are iron phosphate and iron sulfide minerals. On Earth they form through redox cycling, reduction and oxidation reactions. And the most common driver of vigorous redox cycling in muddy sediments is microbial life. Microbes breathe rust the way we breathe oxygen. They create micro-environments that precipitate distinct minerals. The leopard spots on Jezero fall show exactly this kind of patterning. It is a spatial organization that on Earth we associate with biological activity, but science demands caution. The paper uses the term potential biosignature. This is not a claim of discovery, it is a statement of compelling evidence. Alternative abiotic explanations exist, but they are less likely. High-minus temperature processes could create some minerals, but the rock shows no heating signs. The minerals are low-temperature phases formed in cool water. Perhaps the organic molecules came from meteorites. Perhaps groundwater circulation formed the patterns later. But invoking multiple independent processes violates Occam's razor. The simplest explanation that fits all the data starts to point toward biology. The lead author Joel, who wrote C from Stony Brook University, was carefully quanted. He said the combination of chemical compounds could have been a rich energy source for microbes. But just because we saw compelling signatures did not mean we had a biosignature. We needed to analyze what that data could mean. This is the honest language of science at the frontier. We have taken this as far as we can with the rover. The next step requires bringing Sapphire Canyon back to Earth. We need labs that can perform isotopic analysis and high-resolution electron microscopy. We need to rule out alternatives with absolute confidence. Mars sample return was the plan. Perseverance has collected 30 such samples, each sealed in a pristine tomb. But the mission is now in jeopardy. Budget overruns, technical challenges and political pressures have caused delays. Optimistic timelines push sample return to the 20-30s. Pessimistic scenarios say it may not happen at all. So Sapphire Canyon's it's on Mars. The most tantalizing evidence for life beyond Earth is waiting in a tube. We have gone as far as robotics can take us. The next leap demands samples in human hands. Meanwhile, Perseverance continues its mission. It is exploring other parts of Jezero crater, building a broader geological picture. Recent analyses reveal a dynamic history of wet and dry periods. Early Martian fluids were acidic and hostile. Later they became more neutral and hospitable. The Leopard spots of Jezero falls formed during one of these later habitable windows. This is why astrobiology is so challenging. You need the right ingredients at the right time under the right conditions. You need preservation over billions of years. And you need a colossal amount of luck. Despite all the caveats, September 10th, 2020-5 is a historic date. It is the day science officially acknowledged we have found something on Mars that might be evidence of ancient life. Not a false alarm, not a retraction, but a legitimate, carefully vetted potential biosignature. The debate will rage, alternative ideas will be tested. But the reality we confront is this. 3.5 billion years ago, when life was first stirring on Earth, Mars may have been conducting its own biological experiment. The James Webb Space Telescope is not just taking pretty pictures. It is functioning as a time machine peering into the universe's infancy. And what it sees there is forcing a rewrite of all the textbooks. In September, astronomers announced the detection of oxygen in a galaxy called JWST-GS-GA14's era. This galaxy is 13.4 billion light-years away. We are seeing it as it was only 400 million years after the Big Bang. The universe was a toddler filled with primordial hydrogen and helium, yet oxygen was already present. Oxygen is a heavy element. It cannot be made in the Big Bang. It is forged in the nuclear furnaces of stars and scattered by their explosive deaths. Finding oxygen this early means generations of stars had already lived and died. Stellar evolution was already in full swing in the cosmic dawn. The first stars must have formed earlier and burned faster than any model predicted. This is just one of many JWST shocks. The telescope is finding massive mature galaxies everywhere it looks in the early universe. Galaxies that, according to previous models, should not have had time to form. Their sheer size and complexity suggest that structure formation happened at a breathtaking pace. The leading theories of cosmology and dark matter are now under severe strain. We may be missing a fundamental piece of physics in our understanding of the young cosmos. But JWST's revolution does not stop there. It is also a powerful tool for studying exoplanet atmospheres. Using the transit method, Webb analyzes the light of a star filtering through a planet's atmosphere. Different molecules absorb specific wavelengths, creating a chemical fingerprint. Webb has already detected water vapor, carbon dioxide, methane, and even sulfur dioxide in the atmospheres of gas giants hundreds of light-years away. This is not just a catalogue of chemicals. It is a window into the weather and chemistry of alien worlds. For example, sulfur dioxide on a hot Jupiter suggests active photochemistries in its upper atmosphere, driven by intense light from its parent star. The ultimate goal, of course, is to find a true Earth analog, a rocky planet in the habitable zone with an atmosphere containing water and potential biosignatures. Webb is pushing toward that goal. It has studied the atmospheres of smaller rocky planets, like those in the TRAPP, by ST-1 system, though the signals are faint and challenging to interpret. The detection of the Biosignature gas, like oxygen or methane on a rocky world, would be monumental, but JWST teaches us caution. It shows us that abiotic processes can mimic biology. The early universe itself produced oxygen without any life. Understanding the full context of a planet's star and its geological activity is crucial. Beyond exoplanets, JWST is probing the cold structures of our own solar system. It has observed the Kuiper belt, revealing the composition of distant icy bodies. It has studied the plumes of water erupting from Saturn's moon and sunspot. It has provided new insights into the atmospheric dynamics of Jupiter and Neptune. Everywhere it looks, JWST reveals surprise. The early universe was more structured, undevolved than we thought. Planet formation leads to a stunning diversity of atmospheric chemistries. Our cosmic neighborhood is more dynamic and interconnected than we imagined. We are living through a golden age of observational cosmology, and the James Webb Space Telescope is our premier tool for exploring this new frontier. The data it is collecting will keep scientists busy for decades, and every new image has the potential to overturn another long-held assumption. On September 17, 20-5, we confirmed the 6,000th exoplanet, by gas giant orbiting the Sun like star 800 light-years away. The milestone passed with little fanfare, because finding new worlds is now routine. We add dozens to the catalogue every month. The first exoplanet was discovered in 1990-5. It took 30 years to go from 1 to 6,000. This exponential growth is a testament to human ingenuity, but the 6,000 we have found are not a representative sample. Our primary methods are biased. The transit method finds planets whose orbits are edge-on from our viewpoint. The radial velocity method finds massive planets that cause big stellar wobbles. Small rocky worlds in Earth-like orbits are still largely invisible to us. The Vera C. Rubin Observatory will change everything. This ground-based telescope in Chile houses the largest digital camera ever built. At 3.2 billion pixels, it can capture the entire visible sky every few nights. It will create a new view of the universe. For exoplanet science, its power lies in microlensing. When a star passes in front of a more distant star, its gravity magnifies the background light. If the foreground star has planets, they create their own tiny lensing signatures. Microlensing is sensitive to planets at all distances from their stars, including cold distant worlds and free-floating rogue planets. Rubin is expected to find thousands of new exoplanets through this method, finally giving us a true census of planetary systems. But its impact will be far broader. Rubin will discover millions of new asteroids in our solar system, including potentially hazardous objects we have missed. It will detect countless transient stellar explosions and other fleeting events. It will map the dark matter distribution through weak gravitational lensing. The data rate is almost incomprehensible. 15 terabytes of data every single night for 10 years. No human team could ever process this. Artificial intelligence and machine learning are essential. Algorithms will sift through the data stream, flagging the most interesting events for follow-up. This is the new paradigm of astronomy. Humans define the questions and machines find the answers in a sea of information. While Rubin scans the sky from the ground, other missions are focusing on specific targets. The European Space Agency's PLATO missions, scheduled for launch in 2020-6, will specifically hunt for Earth-like planets around Sun-like stars. Its precise photometry will find worlds that are true analogues of our own. NASA's Nancy Grace Ronan Space Telescope will also excel at microlensing, combining its space-based here with Rubin's ground-based survey. We are on the cusp of a statistical understanding of planets. We will move from cataloging individual worlds to understanding populations. How common are solar systems like our own? What is the typical architecture of a planetary system? How many planets in the galaxy reside in the habitable zone? The 6,000th world was a milestone, but it is just the beginning of the true exoplanet revolution. Within a decade we may have a catalogue of tens of thousands of worlds, and within that vast dataset we may finally find the one we are looking for, a pale blue dot orbiting a distant star. For centuries we have studied the universe using light. Every telescope from Galileo's to JWST has collected photons. But in 2015 we opened a new sense. We learned to listen to the cosmos. The Laser Interferometer Gravitational Wave Observatory LIGO detected its first signal. It was the sound of two black holes 30 times the mass of our Sun colliding, a billion light-years away. The detection confirmed 100-year, old prediction of Einstein's theory of relativity. Gravitational waves are ripples in the fabric of space-time itself. They are generated by the most violent events in the universe. When LIGO heard the first chirp, it inaugurated a new field of astronomy. We are no longer just seeing the universe, we are feeling its vibrations. The events we can now detect are breathtaking. Binary black hole mergers are common. We have heard the final deaths spiral of dozens of these dark pairs. Their signals allow us to measure their masses and spins with precision, and in 2017 we detected a different kind of collision, a binary neutron star merger. This event was a multi-messenger bonanza. LIGO and its European counterpart Virgo detected the gravitational waves. Space-based and ground-based telescopes across the globe detected the light. It was a short gamma-ray burst to kill over a flash of optical and infrared light. For the first time we could see and hear the same cosmic event. The scientific payoff was immense. We confirmed that neutron star collisions are the primary cosmic forges for heavy elements, like gold, platinum, and uranium. The gold in your wedding ring was likely born in a cataclysm like this. The next generation of gravitational wave observatories will take this even further. The Laser Interferometer Space Antenna LISA is a planned space-based observatory. Free from the seismic noise of Earth LIS, it will detect lower frequency waves. It will hear the mergers of supermassive black holes at the centers of galaxies. It could detect the gravitational hum from the beginning of the universe. It might even spot the cosmic strings predicted by some theories of physics. On Earth, the Einstein telescope is being designed with 10 times the sensitivity of current detectors. It could hear the gravitational waves from the very first stars and galaxies. Gravitational wave astronomy is still in its infancy, but it is already transforming our understanding of the cosmos. It provides a direct probe of gravity in its most extreme regime. It reveals populations of objects that are dark and invisible to electromagnetic telescopes. It is a testament to human curiosity and engineering that we can build instruments precise enough to measure distortions smaller than an atomic nucleus, and in doing so listen to the symphony of colliding black holes. Across the vast expanse of the universe, the landscape of space exploration is shifting dramatically. While NASA focuses on the Moon and Mars with its Artemis program, another power is making aggressive and strategic moves. China's space agency CNSA is executing a long-term plan with breathtaking speed. That Yangon space station is permanently crewed and expanding. Their lunar program has achieved stunning successes. The Change missions have landed on the far side of the Moon and returned samples. Their next goal is the lunar South Pole. The reason water ice. Data from various orbiters confirms that permanently shadowed craters at the poles harbor vast quantities of water trapped in the regolith. This water is the key to sustainable deep space exploration. It can be split into hydrogen and oxygen for rocket fuel. It can provide air and drinking water for astronauts. It makes the Moon not just a destination, but a gas station for the solar system. China's planned Change -6 and -7 missions aim to directly probe and sample this ice. They are not alone. NASA's Artemis program also targets the lunar South Pole. The Artemis II mission plans to land astronauts there. Private companies are also involved. SpaceX has a contract to develop a lunar lander variant of Starship. intuitive machines and astrobotic, while developing commercial landers. The race is on not just for prestige but for resources and strategic positioning. Whoever establishes a permanent presence at the lunar South Pole will control the most valuable real estate in the inner solar system. But China's ambitions extend beyond the moon. Their Tianwen-1 mission successfully placed a rover on Mars. Their next goal is a Martian sample return mission. This would be a technological feat that so far only NASA has attempted and is struggling to fund. If China can return Mars samples, first the geopolitical and scientific implications are huge. They would set the narrative for the next chapter of Martian exploration. There is a concern, however, about containment. International protocols for handling extraterrestrial samples are strict for a reason. The potential for back contamination, however small, must be taken seriously. Will China allow international oversight of their sample containment facilities? The scientific community hopes for collaboration but fears a solar mission. Meanwhile, in Earth orbit, the International Space Station is aging. Its future beyond 2030 is uncertain. China's Tiangong station is new and modern. They are open to international experiments and even foreign astronauts. For nations locked out of the ISS partnership, Tiangong is an attractive alternative. The United States is responding with its own initiatives. The Artemis Accords are a set of principles for peaceful lunar exploration, but China and Russia are not signatories. They have their own International Lunar Research Station concept. The solar system is becoming a stage for earthly geopolitics. We are witnessing the dawn of a multi-cooler space age, driven by national pride, resource competition, and scientific curiosity. The next decade will determine who controls the strategic high ground of C/S lunar space, and sets the rules for the human expansion into the cosmos. The universe we see with our telescopes is just the visible tip of a vast cosmic iceberg. All the stars, galaxies, and gas clouds account for a mere 5% of the total content of the cosmos. The rest is dark and mysterious. 20-7% is dark matter, an invisible substance that binds galaxies together with its gravity. 60-8% is dark energy, a repulsive force that is accelerating the expansion of the universe. We know they exist because of their profound gravitational effects. Galaxies rotate so fast that they should fly apart. The only thing holding them together is the gravity of unseen dark matter. Clusters of galaxies are filled with a hot X-ray emitting gas. The gravity of dark matter is needed to confine this gas, and on the larger scales the expansion of the universe is not slowing down. It is speeding up, driven by the anti-gravity of dark energy. But what are these dark components? We have no idea. Dark matter is not made of atoms or any known particle. It does not emit or reflect light. It only interacts through gravity. The leading candidate for decades has been WINP's weakly interacting massive particles. We have built exquisitely sensitive detectors deep underground to catch them. So far they have found nothing. Other candidates like axions are now getting more attention, but the direct detection of a dark matter particle remains one of physics' holy grails. Dark energy is even more perplexing. It could be Einstein's cosmological constant, a fixed energy density of empty space, or it could be a dynamic field that changes over time. Current observations from Planck and JWST cannot yet distinguish between the two. The nature of dark energy determines the ultimate fate of the universe. If it is a constant, the universe will expand forever at an accelerating rate. Galaxies beyond our local group will eventually disappear from view. If it is dynamic, it could lead to a big rip, tearing apart galaxies, stars, and even atoms. Complicating this picture is a growing crisis in cosmology. The Hubble constant, which measures the current expansion rate of the universe, can be measured in two ways. One method uses the ancient light from the cosmic microwave background. The other uses relatively nearby stars and supernovae as distance markers. These two methods now give stubbornly different answers. This Hubble tension could be a statistical fluke. Or it could be the first crack in our standard model of cosmology, perhaps pointing to new physics beyond our current understanding. Maybe dark energy is not constant. Maybe dark matter has properties we have not considered. Maybe our understanding of gravity itself is incomplete on cosmic scales. This is the cutting edge of fundamental physics. We are probing the 90-5% of the universe that is completely unknown. The answers will not come easily. They will require ever more precise telescopes, new theoretical ideas, and perhaps a stroke of luck. That the quest to understand the dark universe is the grandest scientific challenge of our time. It is a search for the hidden architecture of reality itself. The search for life beyond Earth is focusing on new worlds. Not Mars with its ancient dried minus-up lakes, but on icy moons orbiting the giant planets. Worlds with vast global oceans hidden beneath frozen crust. Jupiter's moon Europa is the prime candidate. Slightly smaller than our moon, its surface is a cracked and fractured landscape of ice. Beneath this shell lies a salty ocean containing twice as much water as all of Earth's oceans combined. The water is kept liquid by tidal heating. As Europa orbits Jupiter, the giant planet's gravity flexes and squeezes the moon, generating enough internal heat to melt ice. The evidence for this ocean is compelling. The Galileo spacecraft measured an induced magnetic field, strongly suggesting a layer of conductive fluid like old water. Hubble has observed planes of water as vapor erupting from the South Pole. An ESA's Europa Clipper mission is scheduled to launch in October this year. It will perform dozens of close flybys mapping the ice shell and analyzing the composition of the plumes. It will use ice-minus penetrating radar to probe the depth of the crust. Its goal is to determine if Europa's ocean is habitable, but Europa is not alone. Saturn's tiny moon Enceladus is perhaps an even more promising target. It is only 300 miles across. Yet the Cassini spacecraft discovered it is spewing giant geysers of water into space from a subsurface ocean located beneath its south pole. Cassini flew directly through these plumes and made a stunning discovery. The water is salty and contains organic molecules including complex hydrocarbons. Most importantly, it detected tiny grains of silicon grains. The only known process that creates grains of this size is hot water interacting with rock. On Earth we see this at hydrothermal vents on the ocean floor. These vents on Earth are oases of life, thriving without sunlight. The chemistry is perfect for life. Liquid water and organic molecules and a robust energy source. Then there is Saturn's largest moon, Titan, a world shrouded in a thick nitrogen atmosphere. It has rivers, lakes and seas of liquid methane defies. Its surface is covered in complex organic molecules, the building blocks of life, but it is far too cold for liquid water. Could there be a different kind of life, a methane-based biology? We do not know. NASA's Dragonfly mission, a drone-like rotorcraft, will launch in 2020-7 to explore Titan. It will hop from site to site sampling the surface chemistry. The exploration of these ocean worlds is a primary goal for 21st century planetary science. Future missions concepts include melt probes that could tunnel through the ice, or submersibles that could explore the alien seas. Finding life in the dark oceans of Europa or Enceladus would be a discovery of epic proportions. It would mean life is not a rare fluke confined to Earth. It is a cosmic imperative that arises wherever conditions are right. It would mean our solar system is teeming with life, and the galaxy must be a garden of living worlds. A new economic sector is being born in the void of space. For decades, space was the exclusive domain of governments. Now private companies are leading the charge. SpaceX has fundamentally changed the economics of access to space. Its reusable Falcon rockets have slashed launch costs. Its Starship vehicle promises to lower them even further. This has opened the door to a new wave of commercial activity. One of the most ambitious goals is asteroid mining. The resources of the solar system are staggering. Near-Earth asteroids contain vast quantities of precious metals. A single platinum-rich asteroid could contain more metal than has been mined in human history. but the more immediately valuable resource is water. Water is the oil of space. It is heavy and expensive to launch from Earth, but it is abundant in certain asteroids called carbonaceous chondrites. Companies like Astroforge and TransAstra are developing plans to prospect and mine these asteroids. The technology is in its infancy, but the potential is enormous. Water mined from an asteroid can be split into liquid oxygen and liquid hydrogen, the most powerful chemical rocket propellant. This would allow the creation of fuel depots in orbit, turning spaceflight from a 1-way trip from Earth to a journey with pit stops. This is the key to sustainable deep space exploration. The Moon is the first in this new economic sphere. The water ice at the lunar poles is the initial resource target. NASA's Commercial Lunar Payload Services program is already paying companies to deliver payloads. This is not just about science, it is about establishing a market. The goal is to create a CIS lunar economy, where resources are extracted and used in space, reducing our reliance on Earth. This will require new legal frameworks. The Outer Space Treaty of 1960-7 is vague on property rights. It forbids national appropriation, but what about corporate extraction? The United States has passed laws allowing its companies to keep what they mine. Other nations are following suit. This is a legal gray area that will likely be tested in the coming decades. Beyond mining, there is manufacturing. The microgravity and vacuum of space are ideal for certain processes. Growing perfect protein crystals for pharmaceuticals. Creating ultra-pure fiber optics. Assembling giant structures like space telescopes. The International Space Station has been attested for this research. Future commercial space stations from companies like Axiom Space and Blue Origin's Orbital Reef will take this to the next level. We are at the very beginning of the industrialization of space. It is a transition akin to the opening of the New World or the development of aviation. It will be messy, it will be competitive, and it will be transformative. The companies and nations that master this new domain will wield enormous economic power, and humanity will take its first tentative steps toward becoming a multi-minus planetary species. In the early 1950s, physicist Enrico Fermi asked the deceptively simple question, where is everybody? The universe is vast and ancient, with hundreds of billions of stars in our galaxy alone. Many of those stars are older than the Sun. If life and intelligence are common, then the galaxy should be teeming with civilizations. We should see evidence of their existence everywhere, yet we see nothing. This is the Fermi paradox, the profound contradiction between the high probability of alien life and the lack of any evidence. With our new telescopes and surveys, we are finally addressing this paradox with data. The first term in the Drake equation is the rate of star formation. We know that well. The second term is the fraction of stars with planets. JWST and Kepler have shown us that nearly every star has a planetary system. The third term is the number of habitable planets per system. We are finding that Earth-sized planets in the habitable zone are common. We have now constrained the first three terms of the equation. The great unknowns are the biological terms, the fraction of habitable planets where life actually appears, the fraction of those where intelligence evolves, and the length of time such civilizations release detectable signals. These are the filters in the Great Filter Hypothesis. Perhaps the emergence of life is itself incredibly rare, a statistical miracle that happened only once. Perhaps the evolution of complex multicellular life is the bottleneck. Or perhaps the development of technology inevitably leads to self-destruction. These are grim solutions to the paradox. But there are other more hopeful possibilities. Perhaps advanced civilizations are out there, but they are not using technologies we can detect. Our searchers have primarily focused on radio signals, but an advanced civilization might use neutrino communication or something we cannot imagine. Perhaps they are among us, but in forms we do not recognize. Perhaps they have transcended biology and exist as post-biological intelligences. Perhaps the galaxy is a carefully managed zoo and we are in a designated wilderness area. The search is now evolving. SETI, the search for extraterrestrial intelligence, is broadening its scope. Instead of just listening for radio signals, we are searching for technosignatures, signs of technology that would be visible across interstellar distances. These could include city lights on the night side of an exoplanet, atmospheric pollution like CFCs from an industrial civilization, giant megastructures like Dyson spheres that would block a star's light in unusual ways, lasers used for interstellar communication or propulsion. The data from JWST and future telescopes, like the Habitable Worlds Observatory, will allow us to search for some of these signatures. We are also beginning to consider the possibility that we have already seen signs. The interstellar object, the MUA with its unusual properties, sparked debate. Could it have been an artifact, a piece of alien technology? Most scientists are skeptical, but the discussion is now part of the scientific mainstream. The discovery of a single technosignature would be the most important event in human history. It would tell us that we are not alone, that the great cosmic silence is not an empty one. It would revolutionize our understanding of our place in the cosmos. Whether the answer is that we are truly alone, or that the galaxy is full of life waiting to be found, the pursuit of this question is one of humanity's most noble endeavors. We are the universe becoming aware of itself, and we are now starting to look for other sparks of awareness in the dark. The pieces of the cosmic puzzle are now falling into place at an astonishing rate. An interstellar visitor with its impossible properties, the Martian rocks whispering of ancient biology, the infant galaxies seen by Webb that defy our models, the hidden oceans of the icy moons, the gravitational waves from colliding black holes, the new space race for lunar resources, the mysterious dark components of the universe, the silent search for other minds. These are not isolated stories. They are threads in a single grand narrative, the narrative of humanity's growing understanding of the cosmos. We are living through a pivotal moment, a Cambrian explosion of astronomical discovery. Our maps of the universe are being redrawn in real time. Our theories are being stress-minus tested and many are breaking. This is not a time for complacency. It is a time for wonder, for questioning and for exploration. The universe is not what we thought it was. It is stranger, more complex and more alive with possibility. The greatest discoveries are still ahead of us. Perhaps the image of 3-I Atlas will show an artificial structure. Perhaps the Mars samples will contain fossilized microbes. Perhaps a technosignature will be detected next year. We stand on the brink of answers to questions we have asked for millennia. Are we alone? How did we get here? What is our destiny in the cosmos? Stay curious, keep looking up, and subscribe to this channel because we will be here to connect the dots when the next breakthrough shatters our reality once again. Good night.